All right. So we've done atoms, we've done molecules, we've learned about the states of matter. Now we're going to get into how to read that wonderful periodic table. And this, if you understand how to read the periodic table, it can actually tell you a lot about how different elements can react. You'll see some familiar terms we may have talked about before. I mentioned valence electrons previously, a little bit of detail, but not a whole lot. So we're going to get more into valence electrons today. And at the end of this discussion, I will post a seesaw activity for you guys. And on seesaw, it'll be another coloring sheet like we've done before, but I will want you to go through on this. It'll be a periodic table on seesaw that you can color. And I will want you to go through and color code it based off of what we talk about today. So you can see how there's different colors for different areas of the periodic table here. Well, today we're going to talk about why that is, and then that you'll be able to apply that to the seesaw activity as well. Alrighty, let's get started. Well, never mind. Click. There it goes. Okay. So I'm just going to buzz through these review slides real quickly because you're fresh off the taste of what an atom is and what a molecule is and the parts of an atom. You guys are awesome. I know you know this. So remember, an atom is a basic unit, and it has even smaller parts, subatomic parts that are called protons, neutrons, electrons. What? And if we look at the atomic mass, that is the sum of the protons and the neutrons. Remember that. You'll need to know that. So if you haven't quite sunk that into your brain yet, now would be a good time. Okay, so electrons. Electrons are really important when it comes to thinking about the periodic table. So that's why we're highlighting them again today. Electrons, remember, they're negatively charged, and they are located outside the nucleus in the shells or the electron cloud. Remember, each of these little rings you could consider to be a shell or an orbital, depending on which word you're using today. And this whole group of lines is the electron cloud. All right, so valence electrons. I used that term previously, but I didn't super well go into it. That's on me, and also I was waiting for it to be a little bit more relevant to the conversation. So this is an atomic diagram of copper. If you'll notice, it's Cu, not Co. I think it was Latin for cuprium or something like that. I'd have to double check. So that's why it's a Cu. So a valence electron is the electron or electrons that are in the outermost shell. So the innermost, outermost. So outermost shell. So as you can see, there's only one valence electron here for copper. So if we're talking about two different types of atoms bonding together to make a molecule, this is the part that's involved. This is the shell that's going to be directly involved in that, the valence electrons. So if they're, depending on the number of valence electrons, it'll determine how many bonds this element can make, and it will determine how reactive it is. So it's important to know how reactive a particular element is, because you should tread carefully around. Certain elements don't react with a whole lot of anything, and certain elements are very combustible. So you got to be careful around them. So here's our great old periodic table. It's not mentioned in this particular discussion, but the design we have today is thanks to a guy named Mendeleev. So people had been trying to organize this periodic table before, but it wasn't very successful. And mind you, we've added a lot of knowledge to the periodic table since then. We've discovered new elements. And so Mendeleev is the one who figured out how to arrange it, and we've kind of kept his system to this day. And once we do find new elements, like we have done in a fairly large number, we can just kind of fit them in. So the periodic table, it is every element we know of. Some of them are very common, some of them are not very common. Like especially once you get down here and stuff, a lot of these elements are almost theoretical. They only exist in labs for like 2 seconds or less at a time. Like they are barely there, but they technically exist. Okay, so here on Earth, they're not super common, but that doesn't mean elsewhere in the solar system or the galaxy, they're not. So it's good to know that these elements exist, because then we can design instruments to detect them and look for other different signatures on other planets and things like that. But all these elements are the ones that we know of. And the periodic table organizes all of our knowledge of these elements in order by increasing atomic number. And if you remember, that's the number of protons. These are key information things. And generally, it's a general rule of thumb, it does also coincide with an increasing atomic mass. Remember those terms we talked about with the atoms lecture? If you don't remember those terms, maybe pause this and go review your notes and then come back. You're back, okay. So, like I said, the periodic table, it not only tells us everything we know about these elements and how many elements we've discovered and all that, but we can also determine how reactive it is. So here on your screen, you're looking at the atomic information for silicon. Silicon is found in sand. It's actually very common here on Earth. We can use it in electronics as well. So you can think, you know, silicon for your high, super speedy computer motherboards. I'm not a computer person, but silicon is involved in making those. So, quick review. From this is what we see on the periodic table. So from this, we know the atomic number, aka the number of protons, is 14. The symbol is Si. It does happen to follow a logic name, at least in English anyway. Below the symbol is the atomic mass, and below that is obviously its name, silicon. Okay, that's all well and good. We know that. We've talked about that before. So there are different ways to classify things on the periodic table. So this is one way of color coding. If you notice, the one on the first slide had more colors to it, and there's reason for that. So if you look at things that are considered metals, so these are things that are going to be solid at room temperature, with the exception of mercury. Mercury is a liquid because it's got to be different. You know, metals are going to be things like gold, silver, aluminum. These are things that we picture to be shiny. You know, they're sparkly. Ooh. The metals tend to be things we can bend into a wire, like copper wiring is very common, and copper is obviously a metal. Here's Mr. Copper right here. So on this particular color coding of the periodic table, they have anything that could fit under the metal qualifications is blue. And that's a lot of them, right? That's like most of them. Malleable, that's how we pronounce this word, malleable. Basically, it means it can be bent. It can be softened a little bit. Like gold is very malleable. Gold is actually really, really soft for a metal. Like I accidentally, once I had a ring on my finger, it was actually real gold. And I confirmed that when I slammed my finger into a door and the ring became square shaped, because it's gold, it's very malleable. So metals are also good conductors of heat and electricity, which is why we use them in our building projects and in our homes and our wires, things like that. You know, remember they conduct electricity and they're ductile. They do tend to have high densities. So remember that means they sink in water, and they have high melting points. Shh, I'm recording. Shh. They also have high melting points. So that means it's going to take a lot of heat to get that solid metal into a liquid form. So when it comes to reactivity, metals at the bottom left corner are the most reactive. So down here, this is the most reactive. Now, those in the red on this particular color coding are called non-metals. Metals, non-metals. You know, scientists, like I said, super great at naming things. So non-metals don't conduct heat very well. They're not very shiny. This is where you're going to find a lot of gases and things like that. So, you know, you don't picture, you know, the carbon dioxide you're breathing out as being super shiny. For those that are solid, they're going to be very brittle and they're going to break easily. They don't bend. They don't conduct electricity. They have lower density, so that's why it's a lot of gases and they float. They can melt pretty easily and they're not super reactive. So key thing to remember here is reactivity increases left to right. So if we're reading across here, this is going to increase reactivity. So how do those valence electrons play into this? And then there's a little subcategory called the metalloids, and those are the green ones on here. So these are the ones that kind of fit the properties of both metals and non-metals. So they kind of put them in their own category because they're weird enough. So like silicon is a metalloid. It does have some conductive properties. That's why we put it in our electronics. But at the same time, it's also not very malleable and things like that. So it fits both categories. And like arsenic is on here, antimony, things like that. These are kind of like the outcasts of the periodic table. They're like, we don't know where we belong. Help us. You're our only hope, Obi-Wan. All right, so this is something you can think about. These are different things you can find. Hopefully you've seen around or could find in your house. And I want you to think, are they metals? Are they non-metals? Or are they metalloids? So a shiny new Yeti cup. That's those tumbler thermos things we all like. They keep stuff hot and cold stuff cold. So do you think that's made of metal, non-metal, or metalloid? So think about that to yourself and kind of go through each of these as you are thinking. You know, these might be hint future test questions. Just gonna throw that out there. And of course, once we are able to meet officially back in person and things like that again, or as close to in person as we can get, we'll talk about these as well if you have questions. So be thinking about those. Okay, so there's different ways and groups and things like that and how things are organized on the periodic table. Because if you know this, now we're back to more different types of colors. So the first thing we're going to understand on the periodic table is there are 7 periods. And that is where you just read straight across. So this is 1 period. This is 2 periods. Even though there's a gap, it's still on the same period, okay? And then this one's a little bit easier to read because it just goes straight across, right? Because there's not as many gaps. And if you aren't aware, these go right here. This whole row kind of fits in here. That's why we go from 56 to 72 because these numbers kind of fit in there. These are just usually pictured as down below because if we didn't, this periodic table would be obnoxiously long and wide. We wouldn't want to deal with it. So they just kind of do like a quick insert and be like, yeah, this is where it goes. So that way it's much easier to print and read and things like that because obviously that's a lot of elements, right? So when we're going across the period, so we're reading from this way to this way, from left to right, like you're reading a book, the atomic number is going to increase. And usually these who are in the same period are going to have some similar characteristics, but not always. Like hydrogen and helium, they're both gases, right? But there's a difference. One is reactive, one is not reactive. And that's an important distinction to make when we're talking about what you're going to put in your birthday balloons. If you want an example of what happens when you fill a floating object full of hydrogen gas, look up the Hindenburg. It was like a blimp situation because that was all the rage at the time. And they filled it with hydrogen, there was a spark, and suddenly the whole thing caught on fire with people on it. It was a bad deal. So that's why we do it. Let's step away from the hydrogen. It's not good. Hydrogen is also used for rocket fuel. So think about that. So remember we talked about shells or orbitals. If they're in the same period, they typically have the same number of energy shells. And the number will increase as we go down. So then we've got 7 periods, reading left to right. And then we have groups or families. Those terms are interchangeable. And this is where we go down. We're reading the periodic table downward. So this is group 1, this is group 2, so on and so forth, all the way up to group 18. So there's significantly more of them because we have more families, more groups. And everything in the same group, so going all the way down, has the same number of valence electrons, the same number of potential bonds. It could, or not, no, okay, never mind, I'll consider that. Same number of outer electrons. So group 1 over here, it's the most reactive. This is ones that need an extra buddy there to make them more stable, less reactive. Then you get all the way over to group 18. These are often called the noble gases over here. Helium, neon, argon, xenon, krypton. No, I'm not talking about Superman. These are the most stable. That's why we call them the noble gases. They don't react with a whole lot of anything because their outer shells are full. They are happy. Don't bother them. But on the other side, like hydrogen's just looking for a fight. Okay, he's going to go off at the slightest thing. So we look at these numbers and we can determine trends, because that is important in science. We want to find trends. We want to find patterns. So if we're going down the period, so reading the numbers 1 through 7, the number of energy shells or levels is going to increase by 1. So if it's in period 3, there are 3 orbitals, 3 separate rings around that nucleus. That's what an orbital means. There's 3 separate rings. Now, because if you think about it, there's more and more electrons being added with the bigger numbers we get. So we need more places to put them. Now, all the way down on period 7, there's 7 orbitals. There's 7 rings around that nucleus because we need more places to put things, more places to put those electrons. And remember, it's probably more reactive down here because it's going to have openings in that valence electron spot. So if you look at it and compare it, this one is going to be more reactive than this one. I think it's cesium, and then this is potassium. So cesium is more reactive. It's got more openings in its valence electrons. It's got, because it's further down on the period. Now lithium up here is less reactive than sodium. Sodium can react pretty dangerously as well. It also has some openings in its valence electrons like all these do. So that's why these are the most reactive over here. But even within the same group, we can compare reactivity based off the period number. All right, so remember we got groups, and this time we're going 1, 2, 3, 4, so on and so forth, all the way up to 18. So if they're in the same group, they're going to have the same number of valence electrons. So remember the valence electrons, that's what I was talking about. Those are the outer ones that work with other atoms. They form bonds. This is what determines how reactive it is. So group 1 here, like this is where hydrogen, they only have 1 valence electron. But group 15 has 5 valence electrons. So you can pay attention to these trends, and so the more valence electrons it has, the more opportunities it has to form bonds with other atoms, basically, to form a different molecule. So like hydrogen with 1 valence electron, it can only form 1 bond. But nitrogen can form several different bonds because it has 5. Okay, so here's our copper diagram again. So these are all the different orbitals right here, these different layers. So when we are smooshing atoms together, we're creating a chemical reaction, like we talked about with our demo last week. And sometimes that creates a new substance. Like when we combined vinegar and baking soda, we created carbon dioxide, a new substance. That was not a starting reagent. That was not a starting ingredient. So to make this chemical reaction go, we need valence electrons. Actually, movement of electrons is also involved in electricity, but that's a physics lesson, so table that. So remember, reactivity is going to change depending on where on the periodic table we're looking at. So I've used the term making an atom happy before. What I mean is how stable is that atom? You know, because the more stable it is, the less reactive it is, the quote unquote happier it is. So if its outer shell, the valence shell, is full, it's happy. It doesn't want anything else. It'll leave it alone. So group 18, the noble gases, has a full outer shell. They are considered inert because they don't want to bond with their atoms. They're not seeking out friends. They're cool by themselves. They're just like, leave me alone. I'm good. So most of these are That's why we call them noble gases. They just don't react with a whole lot of anything. So hydrogen, like I said, hydrogen is very volatile. It does what it wants. Hydrogen is a great example. It does not have 8 valence electrons. So typically that's going to be the most you're going to find is 8. Obviously, it can't have 8 because hydrogen only has room for 1 other electron. It can only hold 2. So hydrogen's the exception, but at the same time, it's very reactive. So we need to figure out how to make hydrogen happy. So we had unhappy hydrogen, sees little frowny face. He's like, oh, I'm sad, I need a friend. So I don't go explodey. Hydrogen typically bonds with itself. So we get the H2. Remember that subscript is H subscript 2. The 2 is lower than the H. So it can bond with itself. So they each come, one separate hydrogen has 1 valence electron. This hydrogen has 1 valence electron. They come together. They have 2 between them. Now they are stable. It is H2. It is still hydrogen. It is a hydrogen molecule instead of a hydrogen atom, and it is happy. You know, we can see it's got big smiley face now. It's cool. And they're both stable. So it's less reactive. It's not going to have problems down the line. All right, so let's look at our friend oxygen. Oxygen's not happy. He's missing some valence electrons. Right now, he has 6. So if you count them out, 1, 2, 3 on this side, 1, 2, 3 on this side. Remember, the valence is the outer ring. But it's in group 16, so it needs 8. It wants to be stable. So it needs to bond with either one atom that has 2 valence electrons or 2 separate atoms that have 1 valence electron each. So we need 2 more valence electrons to make oxygen happy. There's a couple ways we can do that. So think to yourself, how do we add? What are some ways that we have already actually talked about? If you remember the Mickey Mouse analogy I made before, what molecule looks like Mickey Mouse? Think about that. We want to make oxygen happy. We don't like seeing oxygen unstable. So if you remember Mickey Mouse, it's the water molecule. It's H2O. So we know we talked about hydrogen. He's got a valence electron he can share. So if you put 2 of those, they bring 2 valence electrons to this oxygen, and they all bond together and get the Mickey Mouse shape that we know and love. And it makes a stable molecule that is water. So now oxygen itself is stable, and it's stable because we combined it with 2 hydrogens who are now also stable themselves because they also get a full outer valence. So everybody here, we started with 3 separate atoms who all had openings in their valence orbitals. And once you combine them, we get 1 molecule with full valence. The valence is filled, and everybody's stable. It's happy, it's inert, it's water. You know, water is good. We like water. So this, and of course, it takes that Mickey Mouse shape, and you can see it's got nice, happy faces. And so now this is not a very reactive molecule, and we know that because we have stabilized the valence electrons. So that was an intro into how to read the periodic table. Like I said, we're going to go into this some more, and I will assign a seesaw lesson for you guys. It's a coloring sheet. So do what you did with the last coloring sheet and use those tools that'll be on there and color in the different types of the different types of atoms, excuse me. All right, thank you guys for watching, and let me know what questions you have.